Hello, this is QMG, the quantum mechanics guy, enjoying a wonderful coffee here in the wonderful city of Linwood. I have my recent paper here, my most recent paper. I put it in archives about a year ago. I'm working on another paper right now, which I will show eventually. Now I've been absent for like a year, but I've been very busy doing very interesting research, which I think is very important for the startup companies. Now, this one is about quantum superdeterminism. Now, quantum superdeterminism is the ugly duckling of interpretations because the way usually people, the usual understanding of quantum superdeterminism is that you can imagine that we're in this matrix kind of world where whenever you measure something, somehow everything is arranged so that you obtain a certain value, right? Sounds kind of crazy, right? And that's why quantum superdeterminism is not seen in a positive light. It kind of undermines the scientific method, as Bell and the recent winner of the Nobel Prize said. What is his name? Aspen, yeah. It's a very controversial interpretation, but I think there are also a lot of misunderstandings, and that's what Sabine Hossenfelder has been showing. What I like about Sabine's intake of quantum superdeterminism, she actually proposed an experiment that is falsifiable. Well, some argue that it's not really a falsifiable experiment, but it is at least a different experiment that can lead to different physics. You know, if her experiment shows that there are hidden variables, it would show that something very novel, right, for science. But the idea of superdeterminism is that somehow the way in which you measure something is already constrained to the information that you're trying to measure, right? And the real question is that vicious? That's usually not how Sabine puts the question. Sabine considers superdeterminism to be considers that a lot of people don't believe in superdeterminism because it undermines their free will. I don't think so. I think a lot of serious scientists are concerned about the scientific method, right? Because if you start allowing, think about this one, if you start allowing, an interpretation where everything is arranged to fit what you're trying to, it's already arranged with the information that you're trying to measure, well, that you can do that for anything, right? Right? You can always observe something strange, something that you don't understand, and say, well, my device is correlated with the thing that I'm trying to observe, right? You're gonna, I like to think of the scientific method as a way of making sure no fraudster wants to take advantage of you, right? And superdeterminism, in a way, kind of allows that, right? When taken to an extreme, right? Without restriction. And I think that's the point that Sabine is trying to make, that maybe there is a restricted way of doing that, right? But I don't think Sabine Hossenfelder has made a great point about that. And still, it's not clear. It seems like she has an experiment and she's, adapting her experiment a little further, and she has had debates on YouTube about this matter, and it seems like there's something that is not clear there. And the reason I published this paper is to make the idea of superdeterminism clear, that there is at least a place where you can use the loophole, where you can actually understand what superdeterminism is about, what it is not, and that there can be something useful about it. Now, I use it in a cryptographic sense, right? So I'm going to show you what I mean by that after a little, in a few moments. And I picked the most, I believe, what I believe is the most simple way of showing this, and this is using the famous Merman's GHC machine. I actually made a video, and if you want to check out the previous video, well, you can see what the GHC machine is, if you are not familiar with that. If you are, well, you're gonna find this one very enjoyable. You're gonna see a little loophole that is undermined, I think. And Sabine Hausenfelder has made this very clear, that it is a loophole that is not emphasized. And I think it should be emphasized a little more, right? And this paper sort of shows how that loophole can actually be used in order to show that the usual Bell type of inequality experiments can be undermined if one doesn't take care of that loophole, the superdeterminist loophole. So now I'm going to clarify this. I'm not saying that any experiment that has been done before it's wrong or anything like that. I'm pretty much saying that there is some experiments, like the one that I'm going to show you, where you can actually apply the loophole, think that you have violation of a Bell type of inequality, and yet it doesn't show anything, right? It is important whenever you're using a Bell type of inequality experiments that you make sure that the way in which you measure something is not correlated in any way with the quantum information, right? So I'm going to show you how that can be deceptive in some situation, okay? So let me scroll down. I'm going to show you I think the pictures in this paper speak by themselves. Okay, so this is the Merman's GHC machine, right? And as you can see, I have, you can see two yellow men on the bottom, and you can see one on the top, one blue man in the top. And this is to indicate that there are some researchers doing the settings for this experiment, right? So as you can see, the two on the bottom, their job is to set up their particular equipment to a setting 2. As you can see, let's see if I can enhance this one. Yes, there it is. So as you can see on the left, there are two settings, okay, right in the middle, right here. As you can see, there is a setting 1 and setting 2. So yellow men are going to be setting this 1 to 2, okay? Whatever comes out of this central device. So this central device sends information to A, B, and C. And the three researchers are going to make a selection for their settings. So this one selects 1. This ones can select 2. But then sometimes they arrange their equipments and they both set it 1, right? So the difference between the blue one and the yellow ones is that the blue one always sets it to 1. The yellow can set it to 2, but also, like the blue one, they can set it to 1. But then blue doesn't know. Blue doesn't know if these two guys are going to be setting it to one or the other, right? So the information comes from the central device. So you can say that this information here doesn't know, right, what is going to come out, what is going to happen right in this place. So, and then and if they want to test all, to make sure that all devices, that this can happen in all devices, they can rotate, right? So these two yellow men can take this position, and the blue one can be right here, right? They can rotate. So there are three rotations that they can do to test their equipment, right? And what is going to happen? Well, if you know about Merman's GHC machine, you're going to find out that it is impossible to simulate every single result by programming the information right in the GHC state at the center. Right? You cannot put rules and send the rules to all the devices and obtain the results expected by quantum mechanics by this procedure, right? And of course, the explanation is a little, well, you can read the paper to see if you don't know why that is. Well, you can go to Merman's paper, or go to my previous video and check that out. But this is kind of like a better way of doing Bell type of inequalities, Bell type inequality experiments, right? Because this one, it's less statistical, right? In a way, right? Because because if one fails, then well, if a few ones fail, you know that it's the device, that this is not working. Okay, so everything is clear here. Nothing new, right? It's just I'm just explaining how this experiment can be done, right? Which is, this is a textbook information almost, right? But here's another way of doing the same. Okay, and this is where it gets interesting. That's the next picture here. Okay, so now notice you don't have any researchers here. I substituted the researchers for an actual quantum system. So as you can see right here, there is a device that shoots quantum quanta to the settings, and the settings, based on what comes out of these two, is the setting that is imposed on the settings at the measuring devices. Now, there are two colors that come out of this one. There is the blue and the yellow, right? The blue sets the blue, the yellow sets the yellow. So it's also random, quote unquote, right? Just like the research, just like the previous experiment, right? So here, the previous one, if I can go back, there you go. This one, these two guys are supposed to be making decisions independently of the central device, right? So in this situation, you can say that that the measurement independence postulate applies, right? You don't expect whatever they are doing to be correlated with the information that you're trying to observe. In fact, you can also say the experiment itself is independent of whatever is happening, right? So we're good in this one. But let me show you something interesting. If I go down, if I can go down here. Here's something interesting. Now, here we have a quantum mechanical system imposing the settings on another quantum system, right? So now the question is, can you regard this system to be independent of the other one? And that's where it gets interesting, right? Because you could say, in this case, you could interpret that your quantum information is already correlated in some ways with the information that you're trying to observe, right? Why is that? Well, whenever you have, well, let's look at the evidence, right? We know that if you have two quantum systems, even if they are separated, you can actually consider them to be part of one state, right? There are experiments also, there are experiments that show that you can simulate entanglements of things that have never interacted. It's called swapping. And basically you can set up your quantum system in such a way that in such a way that two of them can seem to be entangled even though they never interacted with one another. So we have evidence that indicates that quantum systems can be just entangled. Okay? Well, in this case, it is possible that the information, we can interpret that the information that is imposing the settings, informing you about the settings, is already correlated with the very information that you are trying to observe. So in this case, you can apply the superdeterminism loophole, right? In this case, not in the other one. Now, there is one more subtlety that is often overlooked, okay? Now, you may have, right here, you might argue and say, well, no, this is not correct, okay? Perhaps you can say, for example, perhaps the information here is, the quantum information here is correlated with this information here, but maybe the way in which you're doing the experiment implies that somehow the experiment is correlated with the quantum information, right? Think about this. Let's think about a typical textbook example of Bell inequalities. In Bell inequalities, when you apply an experiment to when you do an experiment to test whether to see if there's violation of Bell inequalities, you for every setting you do one particular experiment, right? So in those experiments, if the quantum information on the settings were correlated with the thing that you're trying to observe, the entanglement, the information that comes out of the center, then you could say that there is a correlation of every experiment with the quantum information itself, which means that the experiments themselves are constrained like the quantum information, right? That's a subtlety that is often overlooked. But notice in this case, in this particular experiment, that is not the case, right? Because when this one is rotated, when I rotate, as you can see here, I put some arrows. When I rotate this, you have symmetry, right? So if I rotate it, no matter, there are three possibilities, all of them are identical. So that means that you cannot correlate the experiment itself with the quantum information that you're trying to observe, right? So the experiment is not constrained to the quantum information that you're trying to measure in this particular case. Only the assistance system that is imposing the system, right? So in this case, you can actually separate the experiment itself from the quantum system imposing the settings. Something that you cannot do in a typical textbook experiment where you test Bell inequalities, right? So that's what this is. That's why this is cool. Okay. Here is what I believe is it's educational because it shows you where here it's the superdeterminism loophole is not controversial at all because only the settings imposed are correlated with the quantum information, but not the choices of the experimenter. So it's not like I sort of constrained to the, if I set up this experiment on the quantum computer, I'm not constrained in any way, you know, by the way I choose things with a quantum computer in some bizarre way. No, this is just something happening with the quantum computer itself, right? And in fact, speaking of the quantum computer, of course, this one was set up in the quantum computer, and I invite people to set it up. As you can see right here, I have some of the circuits. I'll come back to this one in a second. But right here are the circuits that you can actually do on a quantum computer. Basically, test basically is the equivalent of the picture that I just showed you, right? So the outer qubits, the one on the top, this one here, and the one on the bottom are the assistance systems, and the ones in the middle is the GHC, is a GHC state. And as you can see right here, this is what is the settings that are being imposed. And this mirrors more or less what I show you because the qubits in the quantum computer are space-like separated. It's just a few inches. I mean, it's not a whole lot. I mean, it's not like I'm doing an experiment where I separate things and I'm changing the settings very fast, you know, to rule out that there is no to rule out you know, some kind of communication between them. It's not that kind of experiment, but it's a little like that, okay? It's a cheaper version of that, right? But, you know, this is something that you can actually do in your quantum computer. And what is interesting here is that you can actually observe, you know, what is predicted by the quantum theory. And you can actually say that in this case, the quantum superdeterminism is applicable without violating the principle of measurement independence. So your freedom, in this case, is protected. Everything is just about the quantum system that you're studying, okay? So that's why this is very cool. And now, let me go back to the picture that I passed by. Now here's okay, so now we're cool. We can apply the quantum superdeterminism loophole. But then you have to wonder, okay, how the system was initialized. And this is important in this case, okay? It's not so important in a typical textbook example of a test for Bell type of inequalities. So as you can, what if, let's consider the following. What if whatever is happening here, so So this system right here throws information. The quantum information comes out of this place, goes into these two, these two shooters, let's call them, and then they throw the information to the settings. But let's say that this system right here is connected to another quantum system here somehow. Okay, and this one as well is connected to the other one right here on the top. Okay, so basically there's a connection between this one and the other one, right? So here's a question. Can you say that if you have violation of Bell type of inequalities, well, in this case, is, you know, the inequalities that have to be used are called Merman's inequalities, okay? But let's call them Bell type of inequalities because that's what they are. Can we say that the information is, you know, if we have a violation, can we say that then the information is non-local? Can we just say immediately that? And the answer is, you can say no, right? Why? Because by applying Bell type inequalities, in this case, we haven't ruled out that the system was not initialized in one place, program the information, and deliver the information to all the other ones, right? Because in this case, the information can be preserved, right? It can go from this quantum system to this quantum system, and from this quantum system to this quantum system, right? So you can imagine that right here, there can be some secret program transmitting a code to this one and this one so that they flash in a coordinated manner so that the results of quantum mechanics come out as expected, right? So notice that if we do an experiment with a quantum computer like this, like one that I show you right now, like this, okay? If you obtain a violation to Merman's inequalities, it doesn't show you anything about whether the information is local or not, right? Because if the information, so here are the qubits, let's imagine that, you know, like right here before you start the qubit, if all those qubits were initialized in one location, well, you could regard that, you can say that now the violation to the inequalities really could have been programmed locally before, right? Of course, in general, we know that, that locality, quantum mechanics, you can say that quantum mechanics is not local, right? But in this particular case, we can have a doubt, right? In this particular case, the experiment is not sufficient to show whether the information is non-local or not, even if you have a violation of Merman's inequality. So that's what is interesting about this one, okay? We usually memorize, well, violation of Bell type of inequalities, therefore, you have something spooky going on there, right? Something purely quantum mechanical going on. Well, that is true if you can consider your quantum system to be independent about the manner in which the information, in which the settings were selected. But in this case, you cannot say that, right? See, if researchers are setting by hand, let's say, for example, let's say that they are setting what is going to they arbitrarily choose what is going to be said at 3 different locations. They can be miles away. Okay, then you can say, you know, that you can say that whatever the researchers did is independent of what the other ones, if they were not communicating, right? It would be weird to say that they just coincide in the appropriate settings that were going to be delivered by the quantum system, right? That's weird. That would be a violation of the freedom of choice postulate. But in this case, we have a quantum system making those elections, right? Now, if we don't know how that quantum system was initialized, well, then now we have the doubt about if the information is really independent of the information you're trying to observe is independent of the settings that you're trying to impose, right? So, as you can see, this is very interesting, right? Now, this one has an application, of course, okay? One of the, I guess you can say the application of this is that you can actually create some fake random number extractor, right? See, like, if you think about the practical use of Bell inequalities, is that it tells you that the information that you're measuring, if you have violation of Bell inequalities, is independent. Is random, right? That there is no program that you can set up to get that information. So if you have violation of Bell inequalities or Bell type of inequalities, you can be, you know, you can have assurance that that information is great for, you know, creating passwords, because, you know, there is no observable mechanism to predict the pattern of numbers. So you can say it's pretty much random, right? So in that case, you have that assurance. But in this case, think about that. You cannot say that, right? Because you can conceive this. Let me go back to my picture. See, like if you have a let me go back to this one. Okay, so here you can actually see, this can actually make you believe that you are creating random numbers, right? Right. So you can say that whatever measure at A, right, is either a green or a red. Same thing here, green or red. You may think that the numbers that you're getting here are random, and the numbers here are random, and the numbers here are random. Why? Well, because you can say, well, they are space-like separated. We know that there is no transmission of information among them, right? So you can say, okay, the information, there is no mechanism that can describe what's going on. So we can have assurance that whatever is, you know, happening there is just random information, right? And if you rotate this one here, it gives you, and you're pretty much obtaining what quantum mechanics predicts. You can say, well, look, we have a quantum mechanical system. Therefore, the numbers that you're obtaining are random, because there is nothing has shown that there is transmission of information from one into the other. Okay, great. But right here, if you think about it, you could actually build your device. You can build a fake device, kind of like this one, the one that I show you. like you can actually program this one at the bottom with this one and this one, so that the information is already correlated with the other ones, right? So in this case, if you know that this device and this device were prepared locally by another device, then you can have the doubt that this is random in reality, right? So, like I said before, doing a Bell type, doing the Mermin, doing a Bell type of experiment here, it's not good, right, for ruling out whether the information is local or not. And as a consequence, you cannot have the assurance of randomness. Right? So, well, this is very instructive. I invite people to read this paper. It's pretty readable, and you can actually check out. You can actually download it from Archive. And here's what I want to show you. References and acknowledgement. I sincerely want to thank Mateus Araujo for his valuable criticism of quantum superdeterminism. I invite you to check out this link right here. Okay, or you can just type in Google superdeterminism is unscientific. He actually made a wonderful blog. He has the best criticism of superdeterminism I ever seen. And really, it is his criticisms that sort of inspire me to write this paper. Because right here, you can actually have an application of this superdeterminism loophole in a context that is significant for quantum cryptography, right? And furthermore, it shows you the difference between an experiment that is constrained with the quantum information that you're trying to observe and just the settings being constrained with the quantum information that you're trying to observe. The reason superdeterminism has such a bad rap, I think, is because they usually seeing as, you know, both of those happening necessarily, right? So if one talks about, if the settings, usually this is how the superdeterminism loophole is conceived. If the settings are constrained with the quantum information that you're trying to observe, then that means the experiment itself has to be constrained with the quantum information that you're trying to observe, which means that the researcher sort of is constrained to the quantum information, so that you have no freedom of choice, and that seems kind of crazy, right? But I believe I do a wonderful, you know, I present something persuasive where only the settings, in this case, are constrained to the quantum information, not the experiments themselves. The experiments are satisfy the freedom of choice postulate. And just let me mention this because it's important. Not every experiment is like that, right? The textbook examples that you see are basically show one experimental setup for every setting. And here you don't have that situation, right? So basically I pick my experiments very careful so that I could actually run all the settings with less experiments in a way, right? And of course, I invite people to think of different setups that also work, right? Because I can think of 1,000. I cannot publish all those papers, I can try in the future, to present a few more, like here on YouTube. Probably I won't try to do it in archives. I think one is good enough, right, for archives, and then I'll move on to something else. But I think this is very educational, I think, right? I suggest people should start thinking of setups where the experiments are not constrained to the quantum information that you're trying to observe, only the settings. And as you can see, all these experiments have significance in a small area of quantum cryptography, because you can actually use it to build fake devices, right? Think like this: if you have an adversary and you want to make them believe that they have a device that is safe creating passwords, well, this is kind of like the way to go, right? You present this device, but then you also present a way of selecting the settings, okay? So that even if they put the settings far away, the information in the manner of selecting those settings and the information that comes out of the central device are already correlated. So then you can make that person believe that the information is random, just because the information is separated, and that makes them think that there's no transmission of information from one place to the other, ruling out any classical mechanical mechanism going on. But in reality, you're doing a different trick. Okay? Well, it was great seeing you again. And as always, for those about to quantum, we salute you. See you next time.